Joseph Louis Lagrange, a mathematical virtuoso and celestial mechanic. Joseph Louis Lagrange, a luminary in the realms of mathematics and celestial mechanics, was an Italian mathematician and astronomer who left an indelible mark on the intellectual landscape of the 18th century. Born on January 25, 1736 in Turin, Italy, Lagrange's life was characterized by intellectual brilliance and scholarly achievements that reverberate through the annals of mathematics. Early life and education. Lagrange's journey into the world of mathematics commenced with a childhood fascination for the subject. Originally named Giuseppe Lodovico Lagrangia, he later adopted the name Joseph Louis Lagrange to align with the dominant French language in academic discourse. His early education, marked by private tutoring and self-study, showcased a prodigious talent for mathematics. At the age of 17, Lagrange initiated his formal education at the University of Turin, where he immersed himself in the study of classical languages, philosophy, and mathematics. Guided by innate curiosity and an insatiable appetite for knowledge, he swiftly ascended the academic ranks, garnering attention from leading mathematicians of the era. Departure to Berlin and celestial mechanics. In 1755, Lagrange's academic trajectory took a decisive turn when he received an invitation from the Prussian Academy of Sciences to join as a member. Embarking on a journey to Berlin at the age of 19, Lagrange spent the next 2 decades of his life there, flourishing under the mentorship of renowned mathematicians like Euler and D'Alembert. During his Berlin years, Lagrange made groundbreaking contributions to celestial mechanics. His development of the Lagrangian points, positions in space where gravitational forces result in enhanced stability for smaller objects, laid the groundwork for understanding orbital mechanics. This work had lasting implications for space exploration. Analytical mechanics and the principle of least action. Lagrange's most significant contributions emerged in the realm of analytical mechanics. In 1788, he published his magnum opus, Mécanique analytique, Analytical Mechanics, introducing the Lagrangian formulation. This innovative approach reformulated Newton's laws of motion using generalized coordinates, leading to the development of the famous Lagrangian equations. The Lagrangian equations elegantly describe the motion of systems through a single function, encapsulating the dynamics of the system. This approach proved instrumental in solving complex problems in physics, offering a deeper understanding of mechanics. Lagrange also introduced the principle of least action, a foundational concept stating that the path taken by a system between 2 points in space and time minimizes the action, a mathematical quantity derived from the Lagrangian. Number theory and continued fractions beyond mechanics, Lagrange made significant strides in number theory, exploring the properties of integers and advancing the study of quadratic forms. His work on continued fractions, known as Lagrange's theorem on continued fractions, provided deeper insights into the representation of real numbers and their approximations. Moved to Paris and academic recognition. In 1787, Lagrange left Berlin, responding to an invitation from King Louis XVI to move to Paris and join the Académie des Sciences. This marked a new chapter in his illustrious career, positioning him as a central figure in the vibrant mathematical community of 18th century Paris. Lagrange held prestigious positions, including professorships at the Collège de France and the École Polytechnique. In Paris, he continued his work in celestial and analytical mechanics. Collaborating with Pierre-Simon Laplace, they formulated the Laplace-Lagrange stability criterion, contributing significantly to our understanding of the stability of planetary orbits, legacy, and honors. Lagrange's contributions earned him numerous honors. He became a foreign member of the Royal Society in London and received invitations from prominent scientific societies across Europe. Despite political upheavals in France during the French Revolution, Lagrange's work continued to inspire generations of mathematicians. Various mathematical concepts bear his name, such as Lagrange's theorem in number theory and Lagrange interpolation in calculus. His impact on analytical mechanics is profound, with the Lagrangian formulation remaining a standard approach in classical mechanics courses. Later years and death. In his later years, Lagrange faced personal challenges amid political turmoil in France. Despite these difficulties, he continued to contribute to mathematics until his passing on April 10, 1813, in Paris. Lagrange left behind a legacy that transcends the boundaries of time and space. Conclusion. Joseph Louis Lagrange, a mathematical virtuoso and celestial mechanic, shaped the landscape of mathematics and physics during a pivotal period in scientific history. His contributions to analytical mechanics, celestial mechanics, and number theory elevated him to the status of a mathematical giant. Lagrange's ability to synthesize abstract mathematical concepts with real-world applications has left an enduring imprint on the field. As we explore the realms of celestial mechanics, analytical mechanics, and number theory, we find ourselves standing on the shoulders of Joseph Louis Lagrange, a thinker whose brilliance illuminated the path for generations of mathematicians and physicists. His legacy endures not only in the equations and theorems that bear his name, but in the profound impact his ideas have had on the understanding of the fundamental principles that govern the universe.